So today my talk is going to be about SFINAE and its users. A little bit about me. My name is Karthikeyan Natarajan. I'm a senior software engineer at Rapids Group at NVIDIA. Our group develops GPU accelerated data science libraries for NVIDIA, and it has data analytics, machine learning, and graph, which runs the workloads on GPUs, which is actually quite fast on very large data sets. And I am part of the CUDA data frame library team, which develops the C++ and CUDA library for running the data analytics workload on GPU. So we have Pandas GPU accelerator version and also Spark version. It's an open source library. It's a quite good C++ library. So if you do want to, anybody wants to contribute, they're open to, because we do follow good C++ standards. You'll be able to learn a lot. And today's talk is about SFINAE and its users. What is SFINAE? SFINAE stands for substitution failure is not an error. So this is a template metaprogramming technique that is used for template specialization. This is a rule that is applied during. Sorry, I'm sorry, sharing the wrong screen. Yeah, so when this is a template metaprogramming technique, this is the rule that is applied during overload resolution of function templates. So when a function is called, the compiler looks for functions that match the signature. It instantiates template definitions with type detection. So during this instantiation, if there is any failure due to the type substitution, the compiler doesn't treat it as an error. It moves on to the next template definition and tries to do type detection. Let's look at an example to understand what SFINAE is. Here we have three functions. Here we have three functions. Store. First one takes a template parameter, iter, and its argument accepts a subtype called value type. And there is a second one which actually takes the a pointer and a value as a parameters. And third one is actually a normal function which accepts a int pointer and a value as a argument. Let's see how SFINAE is applied during different calls. So here we have three calls. First one is actually where store a.begin. A.begin is actually a vector iterator. So iterator has a subtype called value type. So when the store is encountered, it tries to goes through the functions. First one, it tries to fill the iterator and then iterator value type. This one actually passes, so this one compiles. The next one is actually a pointer. So vector iterator is actually not a pointer, so it doesn't compile. Similarly, for this is an int pointer that also doesn't compile. Now for the second call, we are passing a.data, which is actually a double pointer. So when it goes to tries to fill it the double pointer in the first definition, it does not have a subtype called value type. So this is actually a failure. But the SFINAE rule kicks in, and the compiler doesn't actually throw an error when it tries to compile this. Then next it goes to the next definition, which is actually a template. It accepts a template pointer. So here we pass double pointer. So this actually compiles. And third one is actually not a double pointer, so it ignores that. So for the second call, the second definition is actually used. For the third call, we pass int pointer. Now the first definition does not apply because the int pointer does not have a value type. But if you see the second call, this actually satisfies the condition. Int star pointer is actually a template star pointer, so this satisfies. And we have the third definition, which is actually normal function int star pointer. So this also satisfies. When a compiler encounters a template function in the normal function, compiler usually prefers the normal function. So the third call actually calls the third definition. So during this, actually we saw actually how SFINAE kicks in. Let's see how where this is used. So so SFINAE is used for template specializations specifically. We know that we can specialize templates using a specific type. So for example, int, char, bool. But SFINAE allows us to specialize a template function for a specific group of types that satisfy a specific condition. This specific condition can be passed as a template argument in this std enable if t. Std enable if actually accepts a Boolean argument. If the Boolean template argument is actually true, it has a subtype called type. If it's false, it does not have any subtype. So that's how it's used for SFINAE. Now this Boolean expression can be anything. So there is a type traits header where it has many Boolean expressions like is integral, is floating point, is arithmetic, is signed. So we can use them to actually to specialize for certain types. Let's look at an example. So this is the common code that you will see in most of the SFINAE codes, where you have the last template parameter as std enable if t, which is enable if colon type star equal to null pointer. Now, if you see, we have two template definitions. First one is actually is integral. Second one is floating point. So first one actually compiles for all the integral types like bool, char, int, long. The second one compiles for double and float. So the when it so we can have a different code in these two template functions, and we can specialize for integral types and double types. So that's how we can specialize for a group of types. Now, do we have to write type templates everywhere? What if we wanted to write a complicated expression that is supported on certain types? What if we want to extend for some future types? That's where we can use expression SFINAE. We'll see how SFINAE can be used to write an extensible template specialized code. Now, this is an expression SFINAE where a return type is declared as decl type of an expression. Now, if this expression actually compiles, T1 plus T2 compiles, decl type will return its return type, and this function will be defined. If not, it is considered as a failure and it doesn't throw any error. For in this example, the operator plus is supported by the struct x. So this function will compile. If you have another struct y which does not have operator plus, it will fail to compile. So to summarize, we saw how template SFINAE is applied on template argument, function arguments, and return types. Std kernel enability allows us to do that. And we saw how expression SFINAE is can be applied for writing extensible template specialized code with decl type keyword. Now, if you want to explore more, there are alternatives to SFINAE like tag dispatch and C++17 feature if const expert and C++20 concepts. Thank you everyone for this opportunity.